Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will see that what is pull up and the pull down resistors. And we will also see that why they are used in the many circuits and how to select the proper value of the pull up and the pull down resistors. So as its name suggests, the pull up resistor pulls up the voltage of the digital pin to the logic high level. And in this way, it prevents that pin from the floating condition. So let us understand this point using one example. So let's say we have one microcontroller and we want to interface one switch with this microcontroller. So as you can see, this switch is interfaced with the one of the input pin of the microcontroller. So as you can see, when this switch is in the closed condition, then it will get connected to the ground. And in this way, this input pin will read the logic 0. But whenever the switch is in the open condition, then the input is connected to the nowhere, or in other words, it remains in the floating condition. So in this condition, the microcontroller can interpret the input as either logic 1 or the logic 0. Moreover, because of the external electromagnetic interference, the input voltage at the pin can change continuously between the logic 1 and the logic 0. So to avoid that, we just need to make sure that when the switch is in the open condition, then the pin does not remain in the floating condition. So the pull-up resistor ensures that the input to the pin remains logic high whenever the switch is in the open condition. So when this switch is in the open condition, then through this pull-up resistor, the supply voltage will get connected to this input pin. And assuming there is almost no flow of current through the input pin, the voltage at this input pin is very close to the supply voltage. And due to that, the microcontroller will sense that input as the logic 1. And whenever the switch gets closed, then the input will get connected to the ground. That means whenever the switch gets closed, then the controller will sense the input as the logic 0. So in this way, the pull-up resistor pulls up the voltage of the digital pin to the logic high. And in this way, it prevents that pin from the floating condition. So with the help of these pull-up resistors, we can interface the switches with the microcontroller. But similarly, we can also interface these switches with the logic gates. So here, one of the input of the NOR gate is interfaced with the switch with the help of the pull-up resistor. And the second input is connected to the ground. So whenever the switch is in the open condition, then through the pull-up resistor, the supply voltage will get connected to the one of the pin. And in this way, the input to that pin is equal to logic 1. Similarly, when the switch gets closed, then through this switch, one of the input will get connected to the ground terminal. Or in other words, the input to that pin is equal to logic 0. So in this way, this pull-up resistor prevents the floating condition of the digital pin and it provides the logic high to the pin whenever the switch is in the open condition. But you may ask, what is the need of this pull-up resistor? To prevent the floating condition, we can also directly connect the input pin to the supply voltage, right? Well, actually, this thing is not at all recommended because whenever you close the switch, then the supply voltage is directly connected to the ground terminal. And because of that, there is a short circuit. And this short circuit can also damage the circuit. So in any case, this condition should get avoided. So this pull-up resistor restricts the amount of current that we are drawing from the supply voltage. And that is the reason we require such pull-up resistors. Similarly, now let us see the pull-down resistor. So this pull-down resistor exactly works opposite of the pull-up resistor. So as its name suggests, this pull-down resistor pulls down the voltage of the digital pin to the logic 0. And in this way, it prevents the digital pin from the floating condition. So here as you can see, the switch is interfaced with the logic gate as well as the microcontroller with the help of the pull-down resistor. So whenever the switch is in the open condition, then the input to this logic gate as well as the microcontroller will get connected to the ground via this pull-down resistor. And because of that, the input to this digital pin is equal to logic 0. Likewise, when the switch is in the closed condition, then the VCC will get applied to this digital pin. And because of that, the supply voltage will appear across this pull-down resistor. That means whenever the switch is in the closed condition, then the logic 1 will get applied to the digital pin. So as you can see, similar to the pull-up resistor, this pull-down resistor also prevents the floating condition of the digital pin, and whenever the switch is in the open condition, then it also pulls down the voltage of the digital pin to the logic 0. So that is the basic function of the pull up and the pull down resistor. So apart from interfacing the switches at the input of the logic circuits, this pull up and the pull down resistors are also used in the many other applications. So let us also see that. So sometimes in the circuits, it is required to interface the logic gates of the different logic families. And as you know, the different logic families operate at the different voltage levels. So in such applications, the open collector gates are used. Similarly, when we want to drive the LED or the 12-volt relay using the logic gates, then also these open collector gates are used. So in short, when we want to drive the devices which is operating at the higher voltages than the supply voltage of the logic gates, then typically the open collector or the open drain gates are used. And with these open collector gates, typically the pull-up resistors are necessary. So first of all, let me tell you briefly about these open collector gates. So in the open collector gates, the output of the IC is connected to the base of the transistor. And here, the collector of the transistor is kept open. So whenever the transistor is in the off condition, then the output of the transistor cannot pull itself to the logic high level. So to pull the output to the logic 1, it requires the external pull-up resistor. So whenever this transistor is in the off condition, then through this external pull-up resistor, the output of the logic gate will remain high. And whenever the transistor is in the on condition, then it brings down the output to the logic 0. That means whenever we have this open collector gate or the open collector IC, then to pulls up the voltage of the output pin, we require the external pull-up resistor. And using this pull-up resistor, it is possible to drive a circuit or the load which is operating at the higher voltages than the supply voltage of the logic gate. Or it is also possible to drive the circuits which requires relatively large driving current. Apart from that, they are also used in the I2C or the I2C communication. So in this I2C protocol, using the pull-up resistor, each line of the bus gets connected to the supply voltage. And on this bus, it is possible to connect the multiple devices, where the one device acts as a master and the other devices acts as a slave. So for a moment, let us consider only one master and the slave device. So in this protocol, internally, each device is connected to the bus with the help of the open drain transistors. So as you can see, with the help of the buffer, each device can sense the output voltage of the each line. And whenever they want to communicate on the bus, then they can communicate by making this transistor on and off. For example, when this transistor is in the on condition, then it will pull the SDA line to the logic 0. So each device which is connected on this bus can sense this line with the help of the buffer. And similarly, by turning on and off this transistor periodically, the master can make this line on and off periodically. And in this way, it can send the clock signal on this serial clock line. So in some other video, we will discuss this protocol in the detail. But in short, these pull-up resistors are also very important part of this I2C protocol. So far, we have seen that this pull-up and the pull-down resistors prevents the digital input from the floating condition. And we have seen that they are also used in the many applications. But the question is how to select the value of this pull-up and the pull-down resistors. And while selecting the value of the resistor, what things we should keep in mind. So typically, the lower value of the pull-up resistor refers to the strong pull-up. So in the strong pull-up, the pin voltage of the digital pin will be close to the supply voltage. And in the worst case of the strong pull-up, we will have the short circuit between the digital pin and the supply voltage. Or in other words, the value of the pull-up resistor is equal to 0. On the other side, the larger value of the pull-up resistor refers to the weak pull-up. That means as the value of the pull-up resistor increases, then the input voltage at the digital pin will be lesser and lesser compared to the supply voltage. So the open circuit is the another extreme case where the pull-up resistor is equal to infinite. So if you want the pin voltage to be close to the supply voltage, then one should select the lower value of the pull-up resistor. But if the pull-up resistor value is too low, then the excessive amount of current can flow through the pull-up resistor. For example, when the switch is in the closed condition, then the excessive current can flow through this path. Let's say the supply voltage is equal to 5 volt and the value of the pull-up resistor is equal to 20 ohm. So in this condition, the 250 milliampere current will flow through this pull-up resistor. And due to this large current, there will be unnecessary power dissipation across this resistor. And if you see any battery driven systems, then in such systems, this additional power dissipation can be the issue. That means we cannot select the very low value of the pull-up resistor. On the other hand, if you select the very large value of the pull-up resistor, then there will be a weak pull-up. And it might happen that the input may not recognize the logic 1 properly. For example, when the switch is in the open condition, then the input pin gets connected to the supply voltage via this pull-up resistor. So far we have assumed that in this condition, the input pin does not draw any current. But actually, there will be some leakage current through this input pin. And because of that, we will also have the voltage drop across this pull-up resistor. So because of this voltage drop, the voltage at the input of the pin will not be same as the supply voltage. Let's say the supply voltage is equal to 5 volt and the leakage current through the pin is equal to 40 microampere. So if the value of the pull-up resistor is equal to 100 kilo ohm, then in that case, the voltage at the input of the pin is equal to 1 volt. And due to that, the logic circuit inside the microcontroller may not recognize it as the logic 1. Because as you know, each digital circuit has certain input range over which the input can be recognized as the logic 1. So if the input voltage is not in that range, then there is no guarantee that the input will be considered as the logic high. So as you can see over here, the input voltage at the input pin is equal to 1 volt. And since it is less than the 2 volt, so microcontroller may not recognize it as the logic 1. So the same thing can also be seen from the input impedance perspective. So far we have assumed that the input impedance of the digital circuit is very large, or ideally it is equal to infinite. But actually each circuit has the finite input impedance. So typically the input impedance of the TTL circuit is in the hundreds of kilo ohms. So if the value of the selected pull-up resistor is close to the input impedance of the circuit, then as per the voltage divider rule, there will be a significant voltage drop across this pull-up resistor. And if the value of the pull-up resistor is same as the input impedance of the circuit, then the input which is appearing at the input pin will be half of the supply voltage. And probably the microcontroller may not recognize it as the logic 1. Because as I said, every digital circuit has the specific input range over which the input can be considered as the logic 1. That means the value of the pull-up resistors cannot be in the hundreds of kilo ohms, particularly whenever you are connecting it with the TTL circuits. Now if you are talking about the CMOS based circuits, then the CMOS based circuits has the very large input impedance, or in other words, the CMOS based circuits has the very low leakage current. So in such circuits, we can select the large value of the pull-up resistor. And the large value of the pull-up resistor is especially useful whenever we are operating such circuits with the batteries. But even with that liberty, when we select the large value of the pull-up resistor, then because of the wire capacitance, the voltage at the input pin cannot rise too fast. For example, if we take this I2C bus, then the wire has its own capacitance and it forms the RC combination with this pull-up resistor. So if the pull-up resistor value is too high, then the capacitor will not be able to charge very quickly. And because of that, the voltage at the bus pin will not change very quickly. So that will limit the maximum speed of the communication. So for the fast switching applications, the large value of the pull-up resistor should be avoided. So typically, the pull-up resistors in the range of 5 kilo ohm to 50 kilo ohm will work for the most of the applications. But the exact range will depend on the peripheral circuits as well as the application. So now, let us take one example and let us see how we can calculate the range of the pull-up resistors which will work for the given circuit. So let's say we have one open collector gate which is interfaced with another gate with the help of this pull-up resistor. So here we want to find the range of the pull-up resistor which will work for the given circuit. So to select that range, we also need to have some information about the sum of the parameters of the logic gates. So these parameters we can get from the datasheet. So first, let us find the maximum allowable pull-up resistor for the given circuit. So whenever the output of this open collector gate is high, then the voltage at this input pin will also become 1. And for any logic gate, whenever the input is high, then it draws some current from the input pin. So in the datasheet, it is typically mentioned as the IIH, that is the current drawn from the input whenever the input is the logic high. So let's say for the given NAND gate, this IIH is equal to 50 microampere. That means this NAND gate will draw this current from the supply voltage. And because of that, there will be some voltage drop across this pull-up resistor. So because of this voltage drop, the voltage at the input pin should not go below the certain voltage, because otherwise the input will not be able to recognize it as the logic 1. So in the datasheet, the minimum input voltage which can be recognized as the logic 1 is mentioned as the VIH. So this VIH is the minimum input voltage which is required at the input pin to be recognized as the logic 1. So let's say for the given NAND gate, this VIH is equal to 2 volt. And let's say the supply voltage VCC is equal to 5 volt. So with these parameters, we can easily find the maximum value of the pull-up resistor. That means Rp max is equal to VCC minus VIH divided by IIH. And in this case, if you put these values, then this Rp max will come out as 60 kilo ohm. So with the given parameters, that is the maximum allowable value of the pull-up resistor for the given circuit. So with this value of the pull-up resistor, the voltage at the input pin will not go below the 2 volt, and the circuit will be able to recognize it as the logic 1. But to keep the certain noise margin, the value of the selected pull-up resistor should be always less than 60 kilo ohm, so that the available voltage at the input pin is always more than the 2 volt. But at the same time, we cannot choose the very low value of the pull-up resistor, otherwise we will have the another issue. So now let us find the minimum value of the pull-up resistor which will work for the given circuit. So whenever the input of the first logic gate will become low, then it will sink the current from the other circuits. So in the data sheets, this current is mentioned as the IOL, that is the current flowing through the logic gate of the output whenever the output is equal to low. So whenever this output is equal to logic 0, then the same will also appear at the input of the next logic gate. That means the input to this NAND gate is also equal to logic 0. Now whenever the input to the logic gate is equal to 0, then from the logic gate, some current will flow towards the input pin. So in the data sheets, this current is mentioned as the IIL, that is the input current which is flowing into the logic gate whenever the input voltage is equal to low. And since the voltage at this node is equal to low, so some current will also flow through this pull-up resistor. Let's say that is equal to IP. So now if we apply the KCL at this node, then this current IP is equal to IOL minus IIL. So now to find the minimum value of the pull-up resistor, let us consider the maximum voltage at this pin which can be recognized as the logic low. So in the datasheet, it is mentioned as the VOL. So let's assume that the voltage at this node is equal to VOL. So here the value of the pull-up resistor should be selected in such a way that the maximum current which flows through the pull-up resistor is not more than this value. Or we can say that this Rp minimum is equal to this VCC minus VOL divided by this IOL minus IIL. So let's say this VCC is equal to 5 volt and the VOL of this logic gate is equal to 0.5 volt. Also let us assume that this IOL is equal to 20 milliampere and this IIL is equal to 1 milliampere. So if we put all these values, then this Rp minimum will come around as 236 ohm. So that is the minimum value of the pull-up resistor which we can use with the given circuit. That means the value of the pull-up resistor should be more than this value, so that the current through this logic gate does not exceed this IOL limit. That means for the given circuit, the pull-up resistor range is between 236 ohm to 60 kilo ohm. So that is how we can select the range of the pull-up resistor for the specific circuit. But usually, if you select the value of the pull-up resistor between 5 kilo ohm to 50 kilo ohm, then it will work for the most of the circuits. Similarly, if you are using the pull down resistor, then while selecting the value, you should keep in mind that it should not be very high or the very low. So if the selected value is too high, then the input pin may not be able to recognize it as the logic 0. For example, if you see this case, then when the switch is in the open condition, then through the pull down resistor, the input gets connected to the ground terminal. And as I said, when the input is logic 0, then from the logic gate or the microcontroller, the leakage current will flow back to the input side. So this current is known as the IOL. So because of this leakage current, there will be a some voltage drop across this pull down resistor. So if the value of the pull down resistor is very high, then there will be a more drop across this resistor. And due to that, the input voltage which appears at the input pin will also increase. So if this input voltage increases beyond the VIL limit, then the input pin may not be able to recognize it as the logic 0. So this VIL is the maximum input voltage which can be considered as the logic 0. That means the value of the pull down resistor cannot be very high. And at the same time, if the value of the pull down resistor is very low, then the excessive amount of current will flow through the pull down resistor. And because of that, there is an unnecessary power dissipation across this resistor. So while selecting the pull down resistor value, we should also consider all these aspects. So I hope in this video you understood what is pull up and the pull down resistors and how to select the value of the pull up and the pull down resistor for the specific applications. So if you have any questions or suggestions, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.